Error estimation is an essential part of statistics and of similar importance as parameter estimation. Measurements result from point estimation of one or several parameters, measurement errors from internal estimation, interval estimation. These two parts form an ensemble and have to be defined in a consistent way. Now, the term measurement error, which is normally used by scientists, is somewhat misleading term. A more precise term is the measurement uncertainty. And we also a common term that is used in the field of statistics is confidence intervals. Now, it's not very clear how error or confidence intervals should be defined. And that is why statisticians have very different opinions on the subject. But we can start with a list that summarizes the properties in the single parameter case which one would like to realize. So, it's a desired properties. So, first of all, error intervals should contain the true parameter with a fixed probability. Second of all, for a given probability, the interval should be as short as possible. Now, the error interval should represent the mean square spread of measurements around the true parameter value. We also require that the definition must be consistent. It is observations containing identical information about the parameters should lead to identical intervals. Now, the error intervals should be invariant and the transformation of the estimated parameter. A computation of the intervals should be free from arbitrary model depending assumptions. And consistent method for the combination of measurements and for error propagation must exist. And lastly, the approach must be simple and transparent. Unfortunately, it is impossible to fulfill simultaneously all these conditions because some of them partially contradict each other. So we'll have to set priorities, and sometimes we'll have to use ad hoc solutions which are justified only from experience and common sense. But under all circumstances, we'll try to satisfy point 4, that is consistency. As far as possible, we will follow the likelihood principle and derive the interval limit solely from the likelihood function. Now, the purpose of error intervals is to document the precision of a measurement. And they are indispensable when we combine measurements. If the prior density is known with sufficient precision, we determine the probability density of the parameters and subsequently the moments. But this condition is rarely fulfilled, that we need not discuss it. Normally we are left with the likelihood function only. So, in the rest of our discussion, we'll assume that the likelihood function is of simple shape, differentiable, with only one maximum and decreasing continuously to all sides. So let's discuss the topic of parabolic approximation. So in the parabolic approximation, the maximum likelihood estimate and the expectation value coincide. As well as the likelihood ratio squared and the variance. So we can also derive the standard deviation from the curvature of the likelihood function at its maximum. For a single parameter, we can approximate the likelihood function by an expression like this. So change in the log likelihood by half corresponds to the second derivative at theta hat. For several parameters, the parabolic approximation can be expressed by and we obtain the symmetric weight matrix from the derivatives. And the covariance or the error matrix from its inverse. In most cases, the likelihood function is not known analytically. Usually we have a computer program which delivers the likelihood function for arbitrary values of the parameters. Once we have determined the maximum, we are able to estimate the second derivative and the weight matrix, computing the likelihood function at parameter points close to the maximum likelihood estimate. To ensure that the parabolic approximation is valid, we should increase the distance of the points and check whether the result remains consistent. And normally, in literature, we encounter statements like the measurement excludes the theoretical prediction by 4 standard deviations. So, and these kind of statements must be interpreted with caution, because validity of such statements relies on the assumption that the log likelihood is parabolic over a very wide parameter range. Neglecting tails can lead to completely wrong conclusions. We also remember that for a given number of standard deviations, the probability decreases with the number of dimensions, as we've seen previously while comparing the normal and the bivariate normal distributions, also the product of two normal distributions. In the coming discussion, we'll address problematic situations which usually occur with small data samples where the asymptotic solutions are not appropriate. Now, we can use likelihood ratio to define error limits, which are usually asymmetric. So, in a 1D case, the two errors, let's call them delta plus and delta minus, satisfy the following relation. So the log likelihood determined at the estimate, the maximum likelihood estimate, minus the log likelihood at theta minus delta minus is equal to, again, the log likelihood at the MLE minus the log likelihood of theta plus delta plus. Both of these should equal half. If the log likelihood function deviates considerably from a parabola, it makes sense to supplement the one standard deviation limits with two separate standard deviation limits to provide a better documentation of the shape of the likelihood function. The complication can be avoided if we can obtain an approximately parabolic likelihood function by an appropriate parameter transformation. Next, we come to the issue of error propagation. In many situations, we have to evaluate a quantity which depends on one or several measurements with individual uncertainties. We therefore have a problem of point estimation and of interval estimation. We look for the parameter which is best supported by the different measurements and for its uncertainty. Now, ideally, we are able to construct the likelihood function. In most cases, this is not necessary and approximate procedures are adequate. The mean of measurements with Gaussian errors let's denote the errors by delta I, which are independent of the measurement, is given by the weighted sum of individual measurements. Where the weights are proportional to the inverse error square. In case the errors are correlated with the measurements, which occurs frequently with small event numbers, this procedure introduces a bias. So the exact method is to add the log likelihoods of the individual measurements. Adding the log likelihoods is equivalent to combining the raw data as if they were obtained in a single experiment. There is no loss of information and the method is not restricted to specific error conditions. In the standard situation, where we do not know the full likelihood function, but only the maximum likelihood estimate and the error limits, we have to be content with an approximate procedure. The likelihood functions which have been used to extract the error limits are parabolic. Then the standard weighted mean is exactly equal to the result which we obtain when we add the log likelihood functions and extract then the estimate and the error. Now we need a method to average statistical data with asymmetric errors. So we need a method which works without knowing the exact shape of the likelihood function. So to this end, we try to reconstruct the log likelihood functions approximately, add them and extract the parameter which maximizes the sum and likelihood ratio errors. The simplest parameterization uses two different parabola branches. Where this delta plus minus both given as that is the parabolas meet at the maximum and they obey this equation. Adding functions of this type produces again a piecewise parabolic function which fixes the mean value and its asymmetric errors. The solution for both the mean value and the limits is unique. The parameterizations varying the width of a parabola linearly or quadratically with the parameter are usually superior to the simple two-branch approximation. So we set minus of the log likelihood the sigma theta is given as twice of delta plus times delta minus divided by delta plus plus delta minus plus delta plus minus delta minus divided by delta plus plus delta minus multiplied by theta minus theta hat. So sigma theta square basically becomes the log likelihood function has poles at locations of theta where the width becomes 0. So our approximations are justified only in the range of theta, which excludes the corresponding parameter values. Before we rely on a mean value computed from the results of different experiments, we should make sure that various input data are statistically compatible. So let's say we compute the weighted mean value of n results. Let's call it theta bar. And we form the sum of the quadratic deviations of the individual measurements from their average, normalized to their expected error square. So we form this chi-square. Expectation value of this quantity is n minus 1 if the deviations are normally distributed with variances delta I square. But if chi-square is sizably higher than n minus 1, then we can suspect that at least one of the experiments has published a wrong value, or what is more likely, has underestimated the error. For instance, when systematic errors have not been detected. Under the premise that none of the experiments can be discarded a priori, we scale up all declared errors by a common scaling factor. And publish this factor altogether with the mean value and the scaled error. Large scaling factors indicate problems in one or several experiments. So similar procedure is applied if the errors are asymmetric, even though the condition of normality then obviously is violated. So for the asymmetric case, we basically form chi-square equals theta I minus theta bar square delta I plus minus square. But again, delta I plus and delta I minus are valid for theta I less than theta tilde and theta I more than theta tilde, theta bar. Now if we have to propagate, so let's discuss error propagation for a scalar function. Of a single parameter. So if we have to propagate the maximum likelihood estimate and its error limits of a parameter, let's say theta, to another parameter, and we should apply the direct functional relation, which is equivalent to a transformation of the likelihood function. So basically this translation from theta to theta prime, transformation from theta to theta prime gives a transformation for the estimate and also for the spread. And we have assumed that theta prime of theta hat is monotonically increasing. If it is decreasing, the arguments of theta prime have to be interchanged. A difficult problem is the determination of the error of a scalar quantity, which depends on several measured input parameters. So if we are looking at the error propagation for a function of several parameters, so basically we're looking at something like theta of a function of vector mu, which depends on several measured input parameters with asymmetric errors. In such a case, we have to eliminate nuisance parameters. If the complete likelihood function is available, we derive the error limits from the profile likelihood function. Now, the maximum likelihood estimate of theta simply theta corresponding to mu hat, and the profile likelihood of theta has to fulfill the relation delta of the log likelihood equals to find the two values of theta for the given delta log L. You have to find the maximum and minimum of theta fulfilling the constraint. The one standard deviation limits are the two extreme values of theta located on the delta log of L theta equals half surface. If the likelihood functions are not known, then the only practical way is to resort to a Bayesian treatment, that is to make assumptions about the PDFs of the input parameters. In many cases, part of the input parameters have systematic uncertainties. Once we have established the complete PDF f of mu, then we can also determine the distribution of theta.